Now let us begin with the lecture series on fluid mechanics 1. We'll come back. Now today's topics we are going to discuss is velocity distribution, velocity gradient, shear stress, velocity gradient relationship, Newton's law of viscosity, Newtonian fluids and non-Newtonian fluids, rheological diagram, fluid continuum and compressibility. These things we are going to study in the today's topic. So yesterday in my lecture I committed an error while discussing the specific weight. So let us make the correction in the earlier lecture. The specific weight, it is defined as the weight of the fluid per unit volume. Specific weight is designated as W, and weight of the fluid upon volume of the fluid. It is denoted as W, and W is equal to weight per unit volume. Weight is a force, and any mass is pulled by the gravitational force is weight. So force or W is equal to mass density into gravitational acceleration. So therefore it is a product of mass density and the acceleration due to gravity. The specific weight is expressed in terms of kilonewton per meter cube or newton per meter cube or dynes per meter cube. For example, specific weight of water is 9.810 kilonewton per meter cube or 9810 Newton per meter cube. So these figures we will use very frequently in forthcoming lectures. Now before moving further, let us understand what is velocity distribution. So at the boundary of the pipe or at the boundary of the channel, the velocity is 0, and the velocity increases as it moves away from the boundary. So in case of pipe, the velocity is maximum at the center, whereas in case of channels, the velocity is maximum at the surface. So let us say the velocity is different at different points. So at the boundary V is equal to 0, and at the surface it is V is maximum in case of one channel, and V is maximum in case of pipe at the center. So Y is the vertical distance and V is the horizontal distance. So dV upon dy, the term dV upon dy, that is change in velocity upon change in distance, vertical distance, is known as velocity gradient. So del V upon del y or dV upon dy is known as velocity gradient. So it is given in the figure that is before you. So in case of pipe, the velocity is maximum at the center. In case of channels, the velocity is maximum at the center, whereas the shear stress is minimum at the center of the pipe. Now let us understand the Newtonian and non-Newtonian fluids. So we know that the velocity gradient is delta V upon delta y. And what is law of viscosity? First of all, we study the law of viscosity. Law of viscosity states that the shear stress is directly proportional to the velocity gradient, and shear stress is equal to some constant into velocity gradient. What is that constant? That constant is reckoned as mu. What is mu? Yesterday we had discussed that is mu is coefficient of dynamic viscosity or simply viscosity. Unless and otherwise specified, our velocity viscosities are always dynamic viscosity. The unit of mu is Newton second per meter square, dynes second per centimeter square. So these things we have already discussed. So tau is equal to mu into du upon dy or delta V upon delta y or dV upon dy. All these things, they are referred as Newton's law of viscosity. Now the fluids which obeys the Newton's law of viscosity, that is tau is equal to mu into du upon dy or delta V upon delta y. So those fluids are known as Newtonian fluids, and those who do not obey the Newton's law of viscosity, that is tau is not equal to mu into dV upon dy or tau shear stress is not equal to coefficient of viscosity into velocity gradient. So that those fluids are known as non-Newtonian fluids, which is given by tau is not equal to mu into delta V upon delta y or tau is not equal to mu into du upon dy, or tau is not equal to mu into dv upon dy. Very simple. The non-Newtonian fluids are those which do not obey the Newton's law of viscosity. We'll move further. So this is the rheological diagram. What is rheological diagram? Rheological diagram is a plot between the shear stress at y-axis and velocity gradient at x-axis. So different fluids we have plotted here. So y is equal to mx. Y is equal to mx means that line which originates from the origin, and it is a straight line. So the fluid which obeys the Newton's law of viscosity, they are considered as Newtonian fluid. So y is equal to mx type line is referred as Newtonian fluid, which is indicated in the blue color. Then the fluids which do not obey the Newton's law of viscosity, so these are the curvilinear line, and it is given as red line dotted. So that is non-Newtonian fluids. Then the line which possesses some yield stress and intercept at y-axis, so that is green line, which is known as ideal plastic, and the curvilinear line which possesses some shear stress, so those substances are known as thixotropic substances. And the line which coincides with the x-axis, that is mu is equal to 0, sigma is equal to 0, and rho is equal to constant, which is definition of ideal fluid. So that line coincides with the x-axis, those are ideal fluids. So therefore, the rheological diagram is a plot between the shear stress tau against the velocity gradient delta v upon delta y. Now, moving to the next. What is fluid continuum? The fluid continuum is a subdiscipline of continuum mechanics which focuses on the behavior of the fluids, which includes the liquid and the gases. The important examples for our everyday life is water and air. So it is a continuous function, the movement of water and the movement of air. It is a continuous function of space and the time. Whatever we breathe, whatever we travel, or whatever we come across with the contact of water, because water is a life and air is also a life. So it is day-to-day mechanism that we respire with the help of air, and we drink water for our survival. So these two things, that is liquid and the gases, it is a continuous function of space and time. So the space is described in terms of xyz coordinates, whereas the time is t. So space is Eulerian approach, and whereas the time is an Lagrangian approach. That aspect will come and we'll study in the topic fluid kinematics. So till this time, you just remember that the fluid continuum is a continuous function of space and time. Now compressibility. Compressibility is the measure of compressible fluid, which is the bulk modulus of elasticity K, which is defined as compressive stress per unit volumetric strain. What is compressive strain? It is change in pressure, that is dP. That is final pressure and original pressure. The difference between the final pressure and original pressure is known as dP. And volumetric strain is change in volume upon original volume, that is volumetric strain. So it is the dP upon dV upon V. It is known as the bulk modulus, and the reciprocal of bulk modulus, that is beta. Beta is known as the coefficient of compressibility. So dP is the change in compressive stress or change in pressure, and dV upon V is the volumetric strain. We will give the negative sign, that is K is equal to minus dP upon dV upon V. Why we are giving negative sign here? Because it acts opposite to the compressive stress. Therefore, we are giving the negative sign here. So that is K is equal to minus dP upon dV upon V. That is change in pressure, that is volumetric, that is compressive stress upon volumetric strain. Again I will repeat, the bulk modulus is equal to minus compressive stress upon volumetric strain. So which is also given as rho into dP upon d rho, that is equal to 1 upon beta. So thank you. Thank you for attending this today's lecture, and tomorrow we'll study the topic on surface tension and vapor pressure. Thank you.